Gentlemen, welcome back to part G of lab number one. Today what we want to do is we want to finally tackle the X error, X STD values in our R part model, or the output of our R part model. If you look here again, when we did our M1 model, right? We know what the complexity parameter is all about, with the relative to the complexity cost. We understand what the end split is. We understand now what relative error is, right? So now the question is, what is X error and X STD? Now remember again, when we set our complexity, our CP equals to 0, our complexity parameter is 0, and we soften our pre-pruning requirements, right? We try to make a massive, highly specialized, highly detailed tree, right? And then we want to prune back. The objective is to find the most optimal CP value that we want to use for our analysis. When we look for our optimal CP value, we actually look for the row that has the smallest X error, right? Where relative error is less than X error, that's critical, right? So relative error should be less than X error. Also, X error should be the smallest, and it should be out of the smallest X errors, because then what we'll have a bunch of X errors. Eventually we'll probably have X errors that in this particular image, in the previous part F, you'll see that we have a lot of X errors that are, let's see if I can pull it up real quick. Let me pull it up right here so you can see. We'll get like the same X error over and over again, the smallest one. Let me pull it up right here. So right here, this is a good example. So if you notice here, this is from slide F, this is from slides lab number 1F. Right, when we have a situation where our X errors are small, we choose the one that obviously first relative error is less than that X error, yeah. Right, so this one, all three of them would be valid because all three of them are less than the X error. The relative error is less than the X error. But then we choose the X error, or we choose the row. We choose the row where that has the least amount of end splits. In this case, 4 is the least amount of end splits. Remember, the idea again is that we want a tree that is general as possible. Right? We want a tree that is general as possible. Right? So, but at the same time, we want a tree that doesn't have too many errors or bias or variance in it. And that's why we choose the X error with the smallest CP value with the minimum amount of splits, which again is going to be 0.1. So this is with line 4, and it's going to be the CP value is 0.015386, right? So given that, if X error is that important, finding the optimal CP value, how do we do it? Right? What is it? What is it actually? The X error is the average error of the 10-fold cross-validation test that happens at every split. The variable X, the parameter, basically xval, we can define this, controls how many folds R part will do. By default, R part will do 10-fold cross-validation test. Now, what is a cross-validation test? A k-fold cross-validation test, or in R part's case, 10-fold validation test, is basically a way to validate what we call the stability of our machine learning algorithm. Stability is defined by, firstly, being confident that our model has gotten most of the patterns from the data correct. Right? That's number one. We're confident that our model has correctly deduced the patterns from the data. In addition, that the model is also low on both bias and variance. What do we mean by bias? Bias is basically when your model is preferring one class over another. In our example, let's say hypothetically it prefers to predict something as setosa versus a versicolor, right? That's bias. In terms of variance, what variance means in the world of tree models is a small change in the data can cause a large change in the final estimated tree. This is something that people usually knock tree models on. The fact that they do suffer from high variance. That if the data changes ever so slightly, that the final tree estimate will change too. If that's the case, then what good is your tree evaluation model, right? To address this, k-fold cross-validation is the technique that is used. Basically, the idea is divide your training data, the data you're using to train a model, divide that into k subsets. Again, in our case, our parts case, that is 10 subsets. One of the k subsets, one of the 10 subsets is then used as the test set. The other k minus 1 or 9 in our case are then used as the training set. A model is created on that training set. It is then, the results are then tested. A confusion matrix is then created using the test set, that 10th piece. The error rate is calculated. It's adjusted according to the base error or root base error like we did before. And that is your adjusted error for that first iteration. But we do 9 other iterations. So the subset we chose is now part of the training set, and now another subset will be used as test data. This happens for every iteration, or in our case, 10 iterations. And you can see, and what happens is we get all these error estimates, we take the average. That average is the cross-validation error. That average is the cross-validation error. Right? And then XSTD is simply the standard deviation of all those errors. As you can see, in our case, we'll get 10 results, 10 error results. And every data point will be in the test case at once, exactly once. Every data element will be used as the test case exactly once. This helps because of the fact that we're using all our data points. This kind of helps not only reduce bias, it doesn't technically, so they say reduce bias, reduce variance. It doesn't reduce bias or variance, as opposed to it illuminates how much bias or variance there is, right? That's the whole idea. It illuminates how much variance or bias there is. And that is why X error, you see how X error goes down? That is a good thing. That is showing, okay, our model is improving both on bias, both on the predictive aspect, and reducing bias and variance. All right, and at a certain point we flatline, and at that point we want to say, all right, choose the one that has the least amount of splits. Again, the one that's the most general, and that is our optimal CP value. That is our optimal CP value to create our model. Okay, so how do we do this now? Well, visually, it's like this. The blue bar right there is considered our 105 rows of training data, right? On my right side, what I do is I break that 105 rows of data into 10 almost equivalent parts. I say almost equivalent parts because you can't divide 105 rows equally into 10 parts, right? So it's okay if some of the data, the subtables are slightly larger than the others. What's more important is that every data point is uniquely assigned to a group, and they're approximately equivalent in the situation. That's okay, all right? So in our first go around, we choose one of the subsets as our test data. The other 9 become our training model. And we basically recreate the analysis that we did before. On our training data, we go ahead and we find the optimal splitting value using the Gini scores. We build a model, a tree, and then we take the test data and run it through the tree. We get the predicted values of that test, and we compare it against the actual values of that test. We get the error rate. Bam, that's our first error rate for when this particular box down here is the test. And then we do it 9 more times. We do it for this when this box is a test case, when this box is a test case, when that box is a test case, and so on, so on, so on, so on, until every one of these orange boxes is used as our test case. After that, we will have 10 error rates, which we take the average of. That is our cross-validation error. That at that point in the tree, that is our cross-validation error. Now, and obviously the standard deviation of this cross-validation scores is our XSTD, our XSTD. So let's go ahead and give it a shot, right? Now, first we want to do is we want to randomly create K subsets. Using data train, we'll randomly split our data into 10 equivalent subtables. They won't be exactly the same. So the trick here is, because we have 105 rows, what you want to do is you always want to divide your data set in by the number of sets of K folds you want to create, or K subsets you want to create. In this case, we want to create 10 K subsets. So we divide 105 by 10. All right, the answer we're looking for is the remainder. What's the remainder of this answer? The remainder is obviously 5. 10 divided by 105 gives us the answer 10 with a remainder of 5. That means that the first five sets will be 10 plus 1. Okay, it'll be 10 plus 1. After that, after the first 5 K subsets, every other K subset will just be 10. That's the generic algorithm that is used to allocate the data fairly. So in our case, the first five sets will be 1, 2, 3, 4, 5 will be 11. And then the remaining 5 sets, which is also 5, the remaining sets, which will also be 5 sets, will be 10. And all together, all in, that'll give us that's how our 105 values are allocated. Now I'm going to go ahead and shuffle the data again as I allocate it. Again, we don't have to, but it's better to randomize the data as much as possible. So I'm going to go ahead and call the sample function again. And remember, the sample function works fairly straightforward, right? If I created a new program here, I will call this say BAML underscore G. I think this is G now. Or I should say BAML lab1 G. All right. And so just as an example, basically sample the way it works. I mean, it's a very nifty function. If I put the number value 10 in here and the value 3 in here, it simply goes ahead and randomly selects values from 1 to 10, 3 of them. So it selects the number 8, 5, and 2. Right? If I were to put 10 in here, it's going to select 10 of values from 1 to 10 randomly, right? Without repeating. By default, it doesn't repeat. All right? So if I wanted to shuffle 10 values, it's a nice way to shuffle the values. All right? So in this case, for sample, I put the first parameter, I put the number of rows in data train, which is going to be 105. The second value is, again, 105 because I want 105 of those values, right? Unique values from 1 to 105. And I put the value, that randomness, into this variable data container called shuffle. And here's the values right here. These numbers, 91, 78, 100, 65, 31, they'll represent the different rows in data train that I'm going to take and put into each subset. So for example, because K1, our first 5 will be 11 values, the 91st row of data train, the 78th row, the 100th row, the 65th row, the 31st row, the 14th row, the 10th row, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to the 3rd row. These rows from data train will go into the K1 value, and they will make up the K1 data set, and so on, so on, so on. And that's what I really do here. If you look at these values right here, grab this, grab one. Oh, that's so annoying. I can't grab any. Oh, there we go. All right. So grab this. That wasn't perfect. All right, that looks horrible. I ungrab it, and I will simply just write it by hand. All that work for nothing. All right, so I have shuffle. right? It's the equivalent of me writing sample 105, comma 105. Same concept. Bam. And now, just like we did here, I'm going to go ahead and do the shuffles. Right, so the first 11 values will go into K1, my data container called K1. Bam, done. If you look at K1, right, 11 rows, and we randomly selected 4 rows. I mean, we randomly select 11 rows throughout data train. And remember, data train itself is shuffled. We just went ahead and shuffled it again. And we want to do this for every one of our little subsets. The first 5 will be 11, 2, 3, 4, 5. All right. And this now turns into 12, 22, 23, 33, 34, 44, 45, 55, right? So each one of these will have 11 values. All right, take one, K5, you confirm, boom, 11. All right, the rest 6 will now have 10 values each. 10 values each. All right. This one is 65. 75, 85, 95, and 105. All right, so now I got my other 10 sets. Bam. All right, so I broke down data train into 10 subparts. And remember, K-fold, you can choose 3 K-fold, you can choose 5, you can choose 10. Our part by default does 10. So that's why we're going through the pain of 10 to show you guys how it's done. Now look, I have these 10 parts. Now the first one, right, is for the root node. The first one is for the root node. The algorithm for the root node is fairly straightforward, okay? Because remember, the way it works is that whatever the training model, the majority species, or whatever the majority value for the root node anyway, for the majority value is amount of items are in the root, in the root node, that's the prediction, right? So in the test data, it predicts the test data to be like that as well. So we'll quickly go ahead and knock that out, and then we'll go back to we'll go to the first split one and how that happens. So this is going to be, for the root, is fairly straightforward, but this part is still going to be the same. We have to create our train data, right? We have to create our train data. So what I'm going to do is I'm going to select K1 to be my first test data, right? I'm going to select K1 to be my first test data. So K1 will be my first test data. Nice. So my training data I'll call K.train, and this will be K2 to K10. I'm going to use a function called rbind. What rbind does is it basically stacks tables one on top of another to make a big table. So if I do K2, K3, right, it's just vertically combining the tables into one table, which is going to be K-train. All right, there we go, boom. So now I got K-train. All right, so K-train is my training data now. Now, I'm just going to go ahead and run the table command on K-train. on species, K train the species. All right. See the breakdown? Okay, cool. Setosa is 23, versicolor is 34, virginica is 37. All right. That means we predict at the root node the training set to be virginica. All right, we predict it to be virginica. The root node error in this case is going to be 60, what is it? 23 plus 34, 67 divided by 105. All right, 67, that's my root node error. 50, I'm sorry, it's 57. 57 divided by 105. All right, 57 divided by 105. 23 plus 34 is 57. Oh, wait, are we missing values here? Oh, yes, of course we are. It's not 105. God, stop it. Right, it's going to be, just do it the right way. Right, so it's going to be 57 divided by, you know, if I just did t equals this, makes my life easier. So I can do the sum of this divided by sum tt altogether. And I got my root node error. All right, 0.60683. Bam. All right, whatever this is. Call it root error or baseline error, guys. Same concept. Alrighty. Alrighty. From here, all right, guys, from here now, what we want to do is we're going to go ahead and now do the prediction on K1. All right, now look, we already said the data at the root node predicted that, look, the data should be virginica. All right. If I do table k.train, not k.train, sorry, k1 species. All right, I predict this should be predicted to be virginica. All right, so all the data in here should be predicted to be virginica. How many are actually virginica? 3. How many are not virginica? Well, Setosa and versicolor are not. That's 4 errors, guys. I mean, that's 8 errors. All right, that's 8 errors. What's my error rate here? It's pretty darn large. It's going to be 8 divided by 11. All right, it's going to be 8 divided by 11, and we're going to divide that by a root error. So my error rate pretty much is, in this case, all right, and then I divide that by my root error. And my first value is 1.19. I'm going to do this 9 more times for my root node, right? Instead of, so look at here. Here is the x error, my first error, x error rate, if you will. So if I were to do x error equals a vector, and then I said, okay, for the first test, the value is whatever this is. All right, so now I record my first value. I get my error rate. And again, it's 1.19. This is why over here, you see this? And we are going to have to obviously take an average of this. This is why the x errors here in the first go around, they're so much larger. Right? They're so much larger. I mean, actually, in this case, it's not that bad at all. It's not that bad at all. But you can notice the standard deviation. So this is where we get these kind of numbers from. And now on my second go, guys, so this is the first go. On the second go now, what I would do, all right, just to show you guys, I would do now, K-train is now going to be K1, K3, K4, K5, K6, K7, K8, K9, K10. K2 is now going to be my test case. I do K-train right here. I do table. Let's do table. K train dollar species. All right, now what? Okay, well now the training data predicts that our test case should be versicolor. All right, because 36 is the largest. All right, it's versicolor. Again, what's my root error rate root node here going to be? It's the same math as before. My root error will be, let's just keep it simple. Equals is going to be 34 plus 24, which is what? 58, divided by the total, which in this case is going to be 24 plus 36 is 60. Yep, 24 plus 36 is 60. 60 plus 34 is 94. Which is right, because the first couple of data sets have 11 values to add up to 105. So all our values should actually end up to, I mean, the first five, as we're doing it, our denominator should be 94. So 58 divided by 94, that is a root error. Okay, from here, what we're going to do is we now look at the breakdown of K2. All right, and again, look at what's happening. We predicted what? We predicted that, according to this, that, hey, this data should be versicolor. All right, cool. What happened again? Versicolor is the least one out of these guys. All right, so versicolor, again, ends up being, the error rate here ends up being, again, it's going to be the 3 and 6 is predicted incorrectly. So it's going to be 9 over, looks like 9 over 11. Right, again, it's going to be 9 over 11. That's going to be our error rate. It's even worse than before. And when we divide our error rate by the root error, we get 1.17-683. And so now x error 2 we have our x error rate 2. And we're going to keep doing this. We would keep doing this until we have all 10. I'm not going to do all 10 because at the root node is fairly straightforward how that's done. You would do this until we have the next one. We would basically do is we would now put K2 back in and take K3 out, do the same function again, get the x error. And once we have all these error rates, right now we did 2. We would take all the values and we would average, oh, hold on. No, this is right. All right, perfect. Yeah, that's better. So, and we would take all the x errors, we would take the average of them, and that average would be our x error. The standard deviation of those 10 values is our xSTD. That's how it works at the root node. All right, that's how it works at the root node. So that's the root node. What happens after that? Well, after the first split, sorry, let's go here. After the first split, right, at the root node, it'll finally do the split. It'll have the x error, it'll have the xSTD values, right? And here you can see it's slightly higher than before, right? That's probably where we're trending, those kind of values. So we'll have the splits, and then it'll have the, it'll do the final split at the Virginica level for all 105 values, and then we'll have a root node error. That main root node error we will now use for the rest of our splits. It was only from the beginning that we were using the root node error for every k value because we didn't have a root node error. We didn't have the root node error at that point. We were using the one at the root level. Now we're going to use our official root node error, which in this case is 65 divided by 105, right? 0.61095, whatever from the other part. And now we're going to go ahead and do our first split. All right, now we're going to do our first split. Now look, we do our first split, and now we got to calculate the x error and all this other stuff. All right. Now to do that, go back down. We're going to do the same thing like we did before. Same thing we did before with our root node, except now, aside from taking the official root node, the root node error, which is 65 divided by 105, whatever that number is, we have to run through all our columns and all our values for each training set, k.training set we do, and we have to find the optimal score and value again. Let's run it by hand. Let's do it by hand for the first, not, well, obviously we're using R, but let's do it manually for the first part. All right, let's do it manually for the first part. And for the first part, again, I already have my K1s, K2s, right? So this would be for the first split. All right, for the first split. All right, for the first split, I'll take my K train as the same one as before. K1 will be my first test case. K through to K2 to K10, again, will be, and again, we can use the same set of K1 to K10s because we're dividing that 105. We're dividing that 105, all right? So K1 will be my test case, K2 to K10 will be my training data. Now, what are we gonna do? Guys, we have to go through and test each of the columns again for the optimal splitting value. So we're going to basically do the algorithm we did in part F again. 10 times. 10 times we have to do it. We'll do the first one. We'll walk through the first one, all right? So you guys get the algorithm. So again, I think our first value is going to be sepal.length. That's the first one, so we'll stick with that. I do my table right here, breakdown. It's easier to see over here. And again, same rules apply. We haven't changed our pre-pruning requirements. We're keeping them the same. The minimum value that meets our requirement is 4.8. At 4.7, the left node child would end up having 6 values, which violates our min bucket rule of 7. Our min bucket rule of 7. And on the higher end, remember, on the higher end, it's always greater than equal. On the lower end, it's less than. So on the higher end, the 7.3 is violated because that would give us greater than equal to 7.3 would be 6 values. So at 7.2, we go up to 7.2. All right, so it's going to be between 4.8 and 7.2. And we go ahead and we can take our function, our code from before. That is not cool. Right, and this is, again, we're just running it back. The difference here, guys, the only difference here is our training data. So firstly, there's two big differences. The first one is our training data, k.train, and that's why I have to make the change here, and I have to make the change here. All right, and the value is now going to be 4.8, 7.2. Excellent, and that's ready to go. All right, create my Gini score vector. All right, and from here, I add my rest of my for loop that I have from before, guys. Hopefully it won't be too bad. That's very bad. I'm going to go back to my previous lab and grab those values. Actually, let me make this a bit smaller. All right. Now again, remember when you're doing this, everywhere here I already made the change. This should be K-train, K-train. Everywhere you see data train, right? And for me, it was line 40, line 41, and line 49. Right? You have to make the change. You have to make the change to K-train from data train. That's it. That's the only difference. For this part, at least. I go ahead, I run this, and I have some sort of value. I'm going to keep doing this. I did it for sepal length. I got to do the other one, guys. I got to do the other ones. All right, so I'm going to go ahead and grab this. If you could automate this a little bit, that'd be nice. All right. Now I need to do for sepal width. Again, I'm going to go to my code that I did before. Sepal width. There it is in all its glory. And it's just easier this way. Oops. Alrighty. Now again, the correct value that I want to choose is not 2.5, it'll be 2.6. At 2.5, it'll be, oh no, 269. What doesn't make a cut? It's going to be 2.6. Excellent. And sepal width will be, at the other end, it should be 3.8. Okay, so that works out fine. All right, notice this, right? Notice this. Data train. That needs to be K train. That's the big difference here. K train, K train, K train. Run that. Boom. All right, nice. And now I need to do for pedal length. Let's go down here, copy this guy. Oops. Ugh, my sensitivities. All right, again, this is going to change to K dot train. This will be 1.5, perfect, up to 6.1, excellent, perfect, perfect. 3, 4, 5, 6. Oh, no, not 6.1, sorry. 1 plus 2 plus 3 plus 4, that's 6. It's going to have to be till 6. 6. Alrighty, and now I can change everything else. K train, what's the K train there? Alright, good, excellent. K train, K train, K train. Alright, now we go ahead and run this one. And guys, again, we're just using the code we did from last week. Alright, I got that one. And now finally, pedal width. I don't know what that is doing here. Oops. Pedal width. All right, guys. Bam. Change this to K-train. Alrighty, and it looks like 0.3 is where we want to be. Excellent. And on the other side, looks like we want to be at 2.3. Excellent. Worked out perfectly. Change that. That, and that. Run this. I got my 4 values. All right, cool. And I have my 4 values that I want. And my numbers here are slightly different than the ones up there because the randomness, again, is different. So the results you're getting from my video might be slightly different than the ones in my slides because it's very different, right? It's very different. Because randomness changes everything. This is why your results are different than mine, guys. This is where the randomness is different. The randomness is different from what I'm doing and what you guys are doing. And if you're run it a couple times, right? So from here, we are now ready for the first k-fold iteration. This is just the first. Oh God, just go ahead and grab these manually. Sepal width, pedal length, pedal width. All right, now I gotta go ahead and run this. All right, so in this case, I do get a unique. This is crazy. So in this case, I do get a unique low impurity Gini score, and that is now in pedal width value 1.8, and I'll go with that. All right, I'll go with that. In my slides, something unique happened, guys. In my slides, something unique happened. In my slides, what happened was my Gini score, if you notice here, for both pedal length and pedal width, was the same. In this scenario, what you want to do is just take the one that has the take from the data set that has a larger distribution of data, as opposed to, in other words, more unique values, as opposed to the column that has more a smaller set of unique values. So there's more iterations of one value versus the other, right? Versus the other. That's why I said, because if the unique values is larger, so pedal length obviously has more unique values. If you go back, see pedal length, you can clearly see it has more unique values than pedal width does. So the numbers there are fairly more equally distributed as opposed to pedal width. You can see some of these numbers are fairly large. So that's why I said in a case where they're both equal, just go in with the higher distribution. But in this case, all right, my Gini score is actually now is pedal width. It by de facto, has the smallest impurity score. I'm going to choose that column, that value as my splitting function. All right, so if that's my splitting function, I'm now going to go ahead and take my test data. What's my test data, guys? We started this party. Minimize this a little bit. We started this test party, remember, back up here in line 14? Yeah, no, sorry. For the first split, line 32, right? It was K through to K10 were my training data. K1 is my testing data. So what am I going to do now? I'm going to go to my K1 data set and now use this model that was defined by K through to K10 to now predict the values on the K1s. Here they are in all their glories. Now, because we are in the first split, it's a fairly, go down here again, it's a fairly simple split. Basically, wherever pedal width is less than 1.8, all right, wherever pedal width is we actually have to look at what the breakdown is. All right, so if I go to my K training set, This is a good point. Let's go ahead and do this, guys. Let's create the right node. I'm sorry, let's do left node first. Equals k train, where the pedal width is less than, remember, when we do less than, it's always less than 1.8. All right, that's the left node. The right node, guys, is going to be k.train, where pedal width greater than equal to 1.8. Remember, the right side is always greater than equal, the left side is always less than. This is how our part does it. Different algorithms are slightly different. This is how our part does it. All right, O train. Can't I spell? Tryon train. All right, now, what is the left node going, oops, sorry again, species. All right, so on the left side, the left node, therefore, is going to be predicted to be versicolor, because the amount of elements that is the most majority in the left node is versicolor. So if the rule here now is very simple, if, for the first split, if pedal width is less than 1.8, then the flower is versicolor. Or to be more exact, the species is versicolor. All right. Else, if it's not less than 1.8, if it's greater than or equal to 8, then this is where we look at the right node. All right. Ooh, that's nice. Virginica by a mile. Otherwise, else it will be Virginica. Otherwise, it will be Virginica. All right. So in this round over here, I have pedal width less than 1.8. I have species versus alpha virginica. Nice. That's my rule. That's my splitting rule, guys. Right? If I did it in, let's see, if I did it using a cool nifty slide for you guys to see, it is basically here. Shape. I'll find green. Right? So this is my 105 values. Nope, not 105 values. I think in this case is 94 values because we're doing the K-fold test. Yep, 94 values. And we'll do this real simple. If it's less than, what do we say? Less than, pedal width less than 1.8. Less than 1.8. True makes it, let's going to do a sloppy line. Yes. Yes. makes it a what? What do we say? It's less than 1.8. Then species is versicolor. Versicolor. Right? Else, no, meaning greater than equal a, it is going to be Virginica. All right, so that's our model. That's our model. Okay, real easy. Now what we're going to do is we go through our K1 data set. Now, finally, our test data, and we apply the rules. In this case, I just have to apply it to what? For my predictions, I just have to apply it to petal width. Petal width. So we can do that real easy. So my prediction is going to be the rows. Actually, we'll do this directly in K1. So K1. Do I want to do that? All right, fine. Let's just say prediction equals K1. I don't want to overwrite K1. So, and now I can say, okay, so wherever, for all the rows, wherever petal width is less than 1.8, for the rows where for the rows where petal width is less than 1.8, make the this is kind of the prediction. I don't want to have the same column name. I'll just say P. P for prediction. It is going to be versicolor. All right, versicolor. Bam. So if I type in predict now, predict table, you see those are all versicolors. Wherever petal width is less than 1.8 is now versicolor. And to finish it off, wherever petal width is greater than or equal to 1.8, make P equal to Virginica. All right. Now we have our predictions. Now what are we going to do? We use the table command to create a confusion matrix, guys. From here, we use the table command to use our confusion matrix. So I will do table. My actual values go first. So I have both the actual values in both the pred table and the K1 table, but just so we stay consistent, species, bam, that's my actual values. And from predict, P, that's my predicted values. Put a little predict right here before them. I run this, bam. What do I have? I have my confusion matrix, and you will notice that what am I missing, guys? I'm missing the Setosa column. I'm missing the Setosa column, right? And the reason I'm missing Setosa column because we didn't make any Setosa. We didn't make any Setosa predictions. We didn't make any Setosa predictions, right? So if you want to see this properly on if I bust out with a Excel sheet, right? Let me copy this over. I think you guys can see this. This is way too small. All right, and this will be Setosa. Versicolor, Virginica, and we just go down the columns, grabbing them. So for Versicolor, it's 440. 440. For Virginica, it was predicted 003. For Setosa, is 0 across the board. Predictions. All right, and now we go ahead and we calculate our error rate. What's our error rate, guys? You guys are pros at this. Go down the diagonal, 7. Sum it by the total number of the values of the whole matrix, which is going to be 11. So 7 over 11 is my error rate for the. No, I'm sorry. 7 over 11 is my accuracy rate. My error rate is going to be 4, the outliers, divided by the total number, which is 11. All right, so 4 divided by 11 is my error rate. I'm going to adjust this according to my official, right? We're doing the math according to our official, whatever our official one is, which I believe from our original model was after the first root, after the first split is 65 divided by 105, right? And we'll just use it as our baseline. Right, and divide this by whatever our baseline is, which is 65 divided by 105. And so after the first iteration, after the first fold, I hate when it reduces it, but whatever, it's fine. 5. All right, boom, right? So this will be 4 divided by 11, right? And the error rate for my first, and basically this comes out to our relative error for our first. It's basically the relative error for our first iteration. It comes out to 0.58. All right, whatever that is, the first split. This is just for when K1 is the testing data. So for K1, when K1 is the testing data, my relative rate was 0.58, relative error. I now have to do it for when K2. I have to do it now for when K2. Let's go all the way back up here. Boom, all right. Let's just scroll down here. So now I have to do a situation where, like we did before, where K1, K3, and the rest of them are going to make K-train data. K2 will be my test, right? I'm going to get that. I'm going to do all that, get the relative error rate, calculate it. Then I'm going to do it again for K2 will be in there. Now K3 won't. I'm sorry, K3 will be my test data, right? I'm going to get that relative error term. I'm going to do it again and again and again. It's going to be 10 times. I'm going to get all those relative error terms, guys. All those error terms. I'm going to take the average of them. That is my cross-validation error rate for the first split. That will go in the second row. The standard deviation of them will be my XSTD. All right, will be my XSTD, guys. That is basically how X error works. That is what's happening there. That craziness, X error, XSTD, that is a craziness. And this is happening behind the scenes. And again, this is why when we are choosing the optimal cost complexity, all right, the CP value to, again, to limit our error, our cost parameter, our error estimation, or our cost of complexity, right? To figure out what our minimum cost complexity should be, or I should say, yeah, the minimum cost complexity should be. This is why we look at the X error rate, because the X error rate takes into account, hey, how good is the prediction going on here, or the pattern catching going on, and how much is the bias and variance? So we can see, look, we can see that early on there's a lot of bias and variance. X error is kind of high, right? And then it gradually falls down. It gradually falls down to something that's more acceptable. And that is how this all comes together with the appropriate CP value. All right, guys? So we'll end the slides here, and I'll post this one up. And the next slide I want to do, the final part I want to do about classification is the loss matrix, which is a very cool, nifty feature in our part in classification and regression trees. Loss matrix is a very cool concept that allows you to favor one type of analysis over the other. I mean, it's similar to how we like to choose recall over precision, but we get more specific as to what we can tolerate as bad predictions and what we can't. Which classes we can tolerate as bad predictions, which ones we can't. So loss matrix is a very cool one. That's going to be, well, I get, what is it? I'm messing up my alphabets now. E, F, G, H. I guess part H will now be loss matrix. And then finally, we can run our data set. We can run our little data set. We can finally run our movie data set that we were trying to do on using classification tree. We can finally do a classification, which again, it won't be that bad. But anyway, guys, so this is the end of the video. I'll see you guys next in class or in our next video. All right, have a good day, guys. Bye-bye.